G'day guys, welcome back. In the last video, we attempted to answer part A of this fairly challenging relative motion problem. And as you can see, we did in fact find the velocity of this pin A just here. Now in this video, I'm going to be trying to answer part B of this question. I'm going to be trying to find the acceleration of pin A just here. And I've copied down some of the most important things we calculated from our previous problem. Okay, well let's pick up where we left off and let's write down the acceleration equation when we're dealing with rotating reference frames. It's the acceleration of A is going to be equal to the acceleration of B plus A rel plus A p relative to B plus the Coriolis acceleration 2 omega cross V rel. This is our acceleration equation, and now what we're going to do is we're going to visually show what each of these vectors look like underneath. So to do that, let's remember that omega that we found from the previous video was 7.39 in the counterclockwise direction. So this was omega just here. Now, I don't know which direction alpha will be, the angular acceleration of this link, but I'm going to assume that it will also be in this direction. And of course, the sign of our answer can tell us whether we're right or wrong by the end of it. Okay, so I'm assuming alpha is going to be in this direction. Now, what does this tell us about the acceleration of point A? Well, we know it must be undergoing a circular path because of this link just here. And so that means it must have a tangential component of its acceleration, which will be facing perfectly upwards, and that will have a magnitude of alpha r. And it will have a normal component of acceleration, kind of hard for me to show in this green, but I hope you can still see it, which will be omega squared r just there. Okay, so let me actually write down both of these vectors that make up the acceleration of point A. You're going to have one component which is perfectly upwards, and you're going to have another component which is perfectly to the left, like this. Okay, so that's the acceleration of point A. Now let's draw the vectors that are making up the acceleration of B. Well, B is quite easy. We know it's going to be 0 because this pin isn't accelerating at all, so AB is going to be equal to 0. Now let's talk about A rel. This is your relative acceleration, and once again, we really don't know whether this pin will be sliding up or down this slot, but I'm just going to assume that it's going to be accelerating down this slot in this direction at this instant. So I'm going to assume that this is going to be A rel. Once again, A rel is just the acceleration of your pin relative to your rotating link just here. So I'm going to assume that this pin is going to be accelerating down this slot at this instant. So if that's the case, then it's going to have, I'm going to draw this acceleration vector A rel like that. Okay, now let's talk about the acceleration of P relative to B. Well, remember, point P is a point at the same position as point A, except it's on the rotating link, right? And now because point P is also undergoing circular motion, that means you can say it will have a normal and tangential component. The normal component will be facing directly towards the center of rotation, point B, and it will be omega naught squared capital R. That's going to be that component, right? But in general, it can also have a tangential component of acceleration here. But read the question carefully, and you'll notice that can't be the case. The slotted link is rotating at a constant angular velocity omega naught, which is 4 radians per second. Right, and because this constant, which is a very important thing, because this is constant, that means it doesn't have an angular acceleration. Or in other words, the angular acceleration is 0. So in fact, there's only one component of your acceleration that makes up P relative to B, and that is purely towards B like this. And that will be omega naught squared R. Once again, in the general case, you would also have a tangential component alpha R as well. And last and least, we've got our Coriolis acceleration. Now, I'll just use orange to describe this. Now, I don't usually like to explain the intuition behind the Coriolis acceleration. I personally prefer to just evaluate the cross product directly. So let's do that. This will turn into 2 times the determinant of I, J, K of omega. Now, omega in this context is actually omega naught. It's the angular acceleration of our object just here. And what direction is it going to be in? Well, it's clockwise, which when you use the right-hand rule using this axis, you can tell it's actually going to be the vector 0, 0, omega naught, right? So in case you need some help with the right-hand rule, place your index finger in the direction of x, place your middle finger in the direction of y. It's a little bit hard to do, your hand goes in a funny way. And then you'll notice your thumb will, by definition of the right-hand rule, be in the positive direction of k. And so if you actually wrap your hand around your thumb now, that is what's considered the positive direction of your angular velocity. And notice that is the positive direction of omega naught. So that means omega naught is going to be positive in the k direction. Okay, I hope I didn't go into too much detail about that. Now let's talk about Vrel. Well, we actually calculated it from the previous video. It turned out it was just this, and it was perfectly in the I direction. So I'll just write it as, rather than, go through it again, I'll just write it as Vrel just here. And it's purely in the I direction, so that means these two things will be 0 just here. And there we have it. We've got our visual understanding of our acceleration vectors. And just to make it clear, I'll actually label this. This was alpha r, and this right here was omega squared r, just like that. Okay, well, let's do the right-hand side first, and let's see where we get. Well, AB, boring enough, is just 0, 0. What about Arel? Well, when we put it into I and j components, it's going to be just Arel in the I direction, and there's no component in the j direction. So that's boring. What about this one? Well, this is just going to be omega squared r, but it's in the negative I direction, so we're going to add that to negative omega naught squared r, and of course none of it's in the y direction like that. And now let's deal with this one just here. Well, it's a little bit annoying. Let's go through the determinant. This will be 2 times by, let's do I first. Let me put a bracket around here. It's going to be I times by 0 minus 0, so it's going to be 0, minus j times by 0 minus omega naught Vrel, so minus omega naught Vrel, and then plus k times by 0 minus 0. So I'll just write that as a 0 just there, okay? All right, so we found the determinant, and let's evaluate this expression just here. Well, if you go through the maths, you can show this must be plus 2 omega Vrel j. So it's going to be plus 2 omega naught Vrel in the j direction. And in fact, you can rewrite that as 0, 2 omega naught Vrel, like that. So right now what I've shown is the entire Coriolis acceleration just boils down into this simple vector, 0 in the I direction and 2 omega naught Vrel in the j direction. So let me actually tidy this up and get rid of this and place this in its stead. There we go, I've filled in the Coriolis acceleration just here. Now to make some space for the acceleration of A, I'm just going to shift everything to the right a little bit. Alright, now we're finally ready to start focusing on the acceleration of A. So to do that, we need to actually break up both of these vectors into both I and j components. So let's do that. This right here will be the j component, and this right here will be the I component. Now we know this angle right here is going to be theta. This is going to be 90 minus theta, which means that we know this right here is going to be theta. So let's actually write the alpha r into I and j components now. We know that the I component will be minus alpha r times by sine theta. And we know that the j component will be alpha r times by cosine theta, like that. All right, so far so good. That's this vector sorted. What about this guy just here? Well, this right here will be its I component, and this right here will be its j component. And we know because theta is defined like this, that means there's going to be a theta just there. So its I component, you can tell, is just going to be omega squared r cosine theta. So this is going to be omega squared r cosine theta, like that. And its j component will be omega squared r times by sine theta, like that. And we have completely deconstructed our acceleration equation into I and j components. This is great. Now we can proceed by analyzing this using algebra. And the way I plan to proceed is to start evaluating j terms first. So just focusing on this bottom row. So let's equate j terms. And what do we get? Well, we'll get alpha r cosine theta plus omega squared r sine theta must in fact be equal to 0 plus 0 plus 0, 0 plus 0 plus 0, won't bother with the colors, plus 2 omega naught Vrel, like this. And so we can actually solve for our angular acceleration of our link directly by just writing this as alpha must in fact be equal to 2 omega naught Vrel minus omega squared r sine theta, all divided by r cosine theta, like that. And if you plug this into your calculator, you're going to get minus 65.66 radians per second squared. Now, before we move on, let's quickly describe what this minus sign means just here. Well, remember, we assumed that the angular acceleration of this link was counterclockwise, alpha. And because this turned out to be a negative quantity, that means that the angular acceleration of this link is, in fact, clockwise. It's the other way around. That's what this minus sign means. All right, now what we could do here is we could then equate I terms just here to solve for your relative acceleration just here. We could do that. There's no problem with going down that route. However, we haven't been asked to do that in the problem. We've just been asked to find the acceleration of pin A. And so we don't need to solve for Arel. We can actually just solve for this green vector right now since we've solved for alpha. So let's do that. The acceleration of A is going to be equal to the sum of both of these vectors, which is going to be minus alpha r sine theta, alpha r cosine theta, plus omega squared r cosine theta, omega squared r sine theta. And if you plug all of this into your calculator, including plugging in alpha is equal to minus 65.66 into here, you will in fact get AA is going to be 20031 I minus 7389 J millimeters per second squared. And there we have it. We have the acceleration of pin A, all calculated for you, deconstructed into I and J components. Now, we could in fact find the magnitude of the acceleration of pin A if we wanted to by squaring both of these terms, summing them together and square rooting, but that's not what we're asked for. We're just asked to find the acceleration of pin A, AA, like this. Alright, so I hope you understood that video, guys. It was a little bit challenging. It involved cross products, determinants, and also deconstructing vectors quite meticulously. But I hope you learned something, and I hope you found it valuable. Cheers, guys.